So today is Professor Abdon Choque-Rivero from Morelia, Mexico, and his title is The Matrix Toda Equation. Abdon, please start.
Thanks, Professor Tunchai, and I would like to thank the organizers for this opportunity. So my take is about the matrix Toda equation. So there are some overview. So we'll speak about some background, moment problems, orthogonal polynomials, zero infinity, about the system of Toda matrix equations and a family of matrix type polynomials. So some background. So we can consider one side Toda lattice system, which is in equality 1, which is equivalent to equality to the system 2. And with the Flaschka transformation 3, it's equivalent to 4. So this stuff is appears in this paper in the bottom by Becker-Stauffer. And we would like to generalize this system 4 in the matrix case and using moment problems methods and orthogonal polynomials. So also we would like to speak about some generalization of the Hurwitz polynomials. We recall that there are polynomial Fn is called Hurwitz polynomial if all its roots are located in the open half hand side of the complex plane. So in particular, we can mention the theorem 16 in chapter 15 by Gantmacher in the book on theorem matrices, which says that a real polynomial of degree n f, which can be written in such a way, so this is h part and g part, is a Hurwitz polynomial if and only if this continuous fraction 5 has the property that the coefficients appearing here is the 0 is positive when n is odd, and 0 and 0 is 0 when n is even, and all the other coefficients should be positive. So we would like to generalize this criteria for the matrix case. It means when the polynomial has coefficients of there are matrices of some dimension q by q. So to do that, we'll say some words about the classical moment problem. Oh, well, the motivation. The motivation is to attain application to the control theory described by block differential equations. Also, we like to have results in robust control. It means a system with certain uncertain physical parameters in the matrix case. So in the scalar case, this stuff is considered in Ackermann, in Haritonov, and we have done some work in the scalar case in these two works, and in the control theory and finite type stabilization, we have these two works here, so which appear in the slide in the bottom of the slide. So this is our motivation. So now some words about the matrix moment problem. So we'll recall that. So let Sn be a sequence of Q times Q Hermitian matrices. So the problem is to find the set of positive measures sigma and interval I such that the equality 6 is satisfied. So in the case when this interval is 0 infinity, it's called the CTS moment problem, the matrix CTS moment problem. And in case when I is the real axis, then it's called the Hamburger moment problem. In the case when I is the finite interval, it's called the Hausdorff moment problem. So for this problem, there are the following subproblems are considered: existence of the solution, the determinateness of this problem, and description of the set of solutions. So we recall that if the solution is unique, then the moment problem is called determined, and if the other case, it's called undetermined. So in the matrix case, the first work was appeared in this work by Crane in 1949. So we use a method. Well, let's first I'll show a picture by Chebyshev, who was the first who considered these moment problems, and then also Stiltes, who was the first. He used for expression moment problems. Here below appears there some of their works. Also, we should mention to Naomi Lisha Hieser and Mark Gregorievich Crane. Hieser worked in Kharkov, and Crane worked mostly in Odessa for former Soviet Union. Well, here are some of their works. So the classical work by Hieser in 1965 is used for many people in moment problems. And also there are some works by Crane. So, well, we use the method by Vladimir Petrovich Potapov. He worked in Odessa and then Kharkov. And his main, well, so we list two of his works. We use some of this, some results of these works in our method. So we also would like to mention Irina Vasilievna Kovalishina. She was a student of Potapov. So now about the existence of the solution. So Stiltes moment problem has a solution if and only if these two Hankel matrices are non-negative definite. So it means here the entries of this block matrices are the moment given. So they are our matrices Q by Q. So we construct them, and if we check that all these matrices for every n are non-negative, then we can assure the existence of the solution. This is for the infinite case. So when if we consider truncated Stiltes moment problem, it means when we have only a finite number of moments of matrix moments, and with the assumption that these block matrices are positive definite, and this problem was solved by Yuri Dukarev in 1981 and 1999. So in the odd case and the even case. So and in the truncated Hamburg-Gellman problem was considered in the case when this block matrix is positive definite, means this one was studied by Kovalishina, and it appears in this work here, which appears in the bottom of that slide. So this is about the existence of the solutions. So now how to obtain the solutions? To obtain the solution, one usually, so if we speak about the truncated Hamburg moment problem, instead of looking for a sigma, then so the measure of the distribution, one looks for the associated function, which is called Stiltes transform, which is holomorphic in the psi minus r, and it has this asymptotic behavior. So in this set, so we also mentioned the Stiltes-Perron inversa formula. Then it means that having the associated solutions, associated function S, we can calculate the measure or the distribution which are associated as. So again, if the moment problem looks for a sigma, then we actually look for the associated function. In that such a way, we pass from these measures to the functions, and then we look for these functions. And actually, these functions play a main role in this investigation, in the studies. So once we have this S, then we can again calculate the measure by using this CTS per inverse formula. So for instance, one example of this measure should be here written in the bottom of the slide, so like that. So this is the truncated Hamburger problem. We consider this for the moment for the explanation of the method. So the method of Patapov. So method from definition one is about the fundamental matrix inequality. So the Patapov method consists on reducing the problem, the moment problem, the looking of the function S, and another problem for of solving some matrix inequality. So we can define S is called the solution of the fundamental matrix inequality if S is holomorphic on the C minus R, and S satisfies this matrix inequality. Then in the next slide I will write who are the entries here. But for the moment we'll say if we had 3 moments, so this matrix inequality will be the has 7. It means we should to solve them. So if we have given 3 moments, then to solve this problem, we should be able to solve this inequality. It means to find this S here. This should be holomorphic. So the theorem one says that S is the function S is the solution of the fundamental matrix inequality if and only if S is the associated solution to the truncated Hamburger moment problem. So I mean, here we're looking here Hamburger because we need only one inequality. So, and here is this inequality again. So we show the HA is actually the this block matrix constructed by the moments. The G Z is here is a polynomial, and B is this matrix block. And the UJ is this matrix block constructed by the moment. So here everything is constructed from the moments and some auxiliary matrices. And the problem is to solve this inequality. So then to solve this inequality, actually one should use the so-called resolvent matrix, in this case for the truncated Hamburger problem. And this resolvent matrix has this form. So these are some metrics. So here because we are assuming that Bloch-Hankel matrices here is positive definite and the inverse exists, and then we can construct this entries of this matrix, which is 2 times Q by 2 times Q, and we can calculate the inverse of this matrix. This resolvent matrix, and then actually it turns out that this inequality here in the second line of the slide is equivalent to this inequality here. So written, but here we should remark that this is here we are using this resolvent matrix, which is crucial here to the solution of this inequality. So in the scalar case, with the help of the entries of this resolvent matrix, we can give the solution like that. It's like Möbius transformation, where we have the entries, and omega is a function of Nevalina type, which can be written in this form. And in the matrix case is similar, but we will look that in the CTS case. So essentially, then this is the method which actually uses this resolvent matrix. This resolvent matrix plays a relevant role in this method, because from that we obtain orthogonal polynomials. We can factorize it, and we can from this matrix we can have continuous fraction and so on. And actually, thanks to this matrix, we can actually then after we will speak about this Hurwitz polynomials. So, well, one some properties of this matrix are the following. So important matrices, properties of this matrix are, we consider the signature matrix. Maybe some researchers call the Pauli matrix. These have these properties, and we call A is J constructive or expansive if these inequalities are whole. And it turns out the similar matrix which we introduced for the hamburger moment problem, it satisfies these inequalities. And well, thanks to this, we could actually explicitly calculate the inverse, which is used in the transformation of the fundamental matrix inequalities. So in this, all of this stuff it plays so an important role is in fundamental equality, which actually connects the T operator or matrix with HJ block matrix and the other matrix which we introduced. So in the former slides. So these are the important properties of this reasonable matrix. And then here for the Stieltjes moment problem, for the matrix case, as said before, Professor Ducar from Harvard University, he made contributions, and he introduced these matrices U as it for odd case and for the even case as in the equality sense 8. And the entries are constructed for the moments as in the hamburger case, but here we have two, we will have actually two fundamental matrix inequalities, and this matrix is in every case when we have an odd number of moments or even number of moments, we have different actually resolvable matrices. So a nice representation of this resolvable matrices are given in 9 and 10. And here we can see that these matrices, which actually are polynomial in zeta, they can be written in such a way that we can see that it's factorized in a nice way. So they are linear in zeta and they are constant and so on. And those in both cases can be written as 9 and 10. So from that we can see that these are related to the so-called Stieltjes parameter, which appears in the book by Ganmacher and Crane in 1850. It's created also with the continuous fraction, the Stieltjes form. These parameters in the matrix case were introduced by Dukarev, and here we have on the left-hand side in the matrix case M0 and L0 as like that, and MJ and LJ are as we see here. They are described in terms of the Hankel matrices and the operators, or the matrix we introduced. And so they are similar, which as in the hamburger. So. Well, this now it turns out that this entries of this polynomials actually are some orthogonal polynomials. So they are polynomials, but we can read as some orthogonal polynomial multiplied by other polynomial. And to do that, we should introduce the orthogonal matrix polynomials. So let be sigma be a q times q positive measure and 0 infinity. We say that the matrix polynomials as written in the slide with q matrix coefficient has degree n if n is non-zero. Finite sequence of matrix polynomials pj is orthogonal. Or it's orthogonal and 0 infinity if with respect to the sigma, if these two conditions are satisfied, means that the degree of pj is a, and this integral is so this condition is satisfied. So here we see the pmt multiplied by the sigma t and tj star. Star means the adjoint conjugate adjoint matrix and conjugate complex conjugate. So, and this is Kronecker symbol, and this is a matrix, so constant. So this is actually, you can write this. This can understand as a scalar product. So this was this about this topic is written well written in this work by these three authors, and also by Duran and Lopez Rodriguez in 2007. So, and others. So we mentioned here below. Well, in our case, we are interested in the orthogonal polynomials and zero infinity. And here we say that sequence, this sequence as here written are positive definite if these block-Hankel matrices are positive definite. In such case, we could define these polynomials as here written in 11 and 12, also here in case 0, where here we specify who are these matrices. So U1J is this one, so on and so on, and here appears JR, the polynomial matrix, and here there are some other matrices which are related to the moments, to the given moments. And then here in year 13, we define the so-called Schur complement. And we will use the Schur complement in the future. So, and we have proposition here, the polynomials P1J and P2J are orthogonal polynomials with respect to sigma and T sigma respectively. So more precisely, the 14 is satisfied. It means that actually we have a scalar product. So it's 0 in case J is not equal to L, and it's with this Schur complement in case J and L are equal. So this is the so in the matrix case, you could understand this as a scalar product of matrix polynomials. So here in this equality, the matrix, we see that actually the matrix, the resolvent matrix, can be written with the help of these orthogonal polynomials, as we said, and it turns out that actually this resolvent matrix will give us the solution, so as written here above. So this here is written F of zeta, and this is actually this is a matrix here, and there's the inverse. So in the right. So and Q, P, Q are certain parameters, set parameters we will introduce in the next slide. So, but for the moment we can look at this matrix, which is resolvent matrix, and we can consider the matrix Q1n star, so times P1 star minus inverse. That means that this turns out this could be written as this continuous fraction. So here appears the so-called Stieltjes-Dukarev parameters, which in the matrix case, in the scalar case, they are called Stieltjes parameters. So there we'll see that actually there are solutions, special solution of the moment problem, Stieltjes moment problem. And here we have another solution, another external solution. Also, it can be represented as a continuous fraction. So all this was written in this work here. So this equalities. So now about this this non-negative pair. So this non-negative pair is used to describe the set, the complete set of solutions in the truncated Stieltjes moment problem. For that, we need this set. There are a couple of Q times Q matrix valued functions. They are meromorphic, say minus zero infinity. And this pair should satisfy these three conditions. So, and then actually we could use some equivalence relation, and then with the help of this matrices, actually we can keep the solutions of the set of solutions as is written on the upper, so in the half of the slide. So as mentioned before, this we have the solutions in the case, and the odd case will be this one, the associated solution. We have the resultant matrix here, and the PQ appears as is written here. So if we choose PQ as written here, then we have a special solution as already said. And if we choose P equal to 1, Q equal to 0, we have the other extremal solution. So this solution will appear when we will talk about the how orbits polynomials. So now some propositions will also, this proposition we will use on the next slides. So here, but we could mention the following. So we know that the moment the matrix LG as we constructed, they are actually constructed with the moments. Now the question is here, the question here we consider is how to recover from the L the moment. So it means actually it means that. So here in the right hand side we have certain continuous fraction. In the left hand side we have polynomials, and the polynomials are constructed by the moment. So, but we would like to recover from the right hand side the moments of the left hand side. So this is actually the interest. So this is down here. So if we have two sequences of matrices which are positive definite Hermitian, and we define the sequence as in 17 and 18, then it turns out that this sequence constructed will be a Stieltjes positive sequence. It means that from this sequence we can construct a polynomial. So, and so we use this equalities 19 and 20, which actually and so we have some relation, explicit relation between the Schur complements and the Duker-Stieltjes parameters, which are important for our studies. So these results were appearing in this work here in the bottom of the slide. And well, for so a little bit about the proof is since these two metrics are positive definite and they are positive definite, from that we have then the block metrics are positive definite, and recursively actually then we prove that the H1J and H2J are positive definite. So from that we have already done that, since these two metrics, block metrics H1J, H2J are positive definite, then we can speak about the existence of this resolution of this correspondence Stieltjes moment problem. So here the lemma is just to explain what we mean by this equivalence of these inequalities. So it's actually this here written about the Schur complement. So now one example. So for instance, if we have in the left hand side we have given this continuous fraction. So and we recover the moments here as here written, and the forms we can construct the polynomials. So we use these relations here. So actually then this C0, ZD, actually these are the coefficients here on the left hand side in the example. And we recover, and actually 23 and 24. So they are here, there appear some coefficients C0, ZD, or ZK, and actually are the same as here in the 1920. So because of the unicity of the solution of the external solutions. So well, here again we say that these equalities can be proved using this Duker representation resolve the matrix in the factorized form. So now we are interested in moment problems which depends on the parameter. So it means using the self-transform. So we let be a sigma monotone, the non-decreasing matrix function, such that equality satisfied. And for alpha bigger than equal to 0, we define these moments. So actually there's a still transform. So that, but now we have some dependence over moments. And we also construct that as in the previous slides, H and J, and all the stuff we have spoken will be valid. Just in this now, we will have a dependence of in lambda and alpha mean. So for instance, an example, if we have this distribution as in 31, the moments will be given 32. So, and we can calculate the block matrices of these moments will be positive definite matrices. So about this matrix distribution, positive, so in matrix case, which is considered by Professor Berg and co-authors in this work. Well, some words about this Stieltjes transform of this so perturbed measure. So a sequence of matrix, depending on alpha, is called Stieltjes positive. The Hankel block matrix is this H1, J, H2, J are positive definite. And then we could consider well, a problem given these moments now. We find the set of positive measures in such a way that the moments are satisfied, and for that we consider this function as in the past. We consider this function, which is called the Stieltjes transform on this distribution, and we also can start. We could look at some relations, asymptotic relation of the Stieltjes transform, depending on lambda. This in the 34 appears the Stieltjes transform and the relation with the moments. So, and we here in 35 we see one relation between the derivative with respect to alpha. So it's equal to this to the right hand side. So also we have another relation here of the Stieltjes transform. So well, we are interested actually in the behavior of the Schur complement. So we recall the Schur complement here, in this case, depending on alpha, as 36, 37. We also recall that these Schur complements in the scalar case can be calculated using the determinants of the block matrices as in 4 and 38. So now the definition, we define the so-called coefficients A and B. Actually, they are called three-term recurrence relation coefficients, because this matrix defined in definition 4 satisfy this here this discrete linear system. And actually, it could be proven that by using the scalar product matrix case that this matrices satisfy this equality. So, by the way, this discrete system, linear system, is for many authors used as a starter or central point, but also for other people. So, as they studied this system as an operator, Jacobi operator. So in this case, in the matrix case. So, but we are interested in the behavior of these matrices in the sense of the Toda equation. So it means that it turns out. So again, here some relation between this matrix. So in the scalar case, these numbers then could be written with the help of these determinants. So here the Toda matrix. So system actually, then in lemma 2, we have a certain relation which satisfies these Schur complements. We have the derivative in alpha, This is 40, 43, 44. So with these equalities and other other identities, we can prove theorem 3, which was our goal, to have this differential equation. It means that this matrix is defined in definition 4. So they satisfy this system on equalities as 45 to 47. So this and all these equalities were proved using, as I said, using identities, and actually we use moments and Schur complements only, not actually we don't use operator stuff or even orthogonality. So we use identities. Oh, for the identities comes as consequence of orthogonality, but we don't use directly orthogonality. So this work was done in this work, and so shown at the bottom of the slide. Now, with this stuff, we like to to relate to the certain matrix polynomial. This will be a matrix polynomial as in the star. So here Fn is so polynomial degree n, and A0 alpha to AN alpha, they are matrices. So we say that if the degree of Fn is n, if A0 is non-zero for alpha 0 to infinity, and we suppose they are determinant non-zero. And we define this in 48, 49, the h part and the j part of the polynomial, and Fn can be written as here in this relation. So, and so for writing shorter, we define this that h over b actually is a times b inverse. So then we can introduce the so-called Hurwitz type matrix Hurwitz type polynomial if there exists two sequences of non-negative matrices such that this representations 50 and 51 exist. So again, so we say that Fn is called a matrix Hurwitz type polynomial if there exists two sequences such that this representation 50 and 51 that it is exists. So they are rate of these two. Actually, there's a Gn times inverse of Gh, and this also this is matrix. It's a matrix a continued fraction. So this is our generalization of the second slide when we recall the book by Ganmacher. So, but now it's in the matrix case. So now what we want to do? This actually want to consider this matrix in this, and we like to see some properties and actually to say if this matrix is Hurwitz or not in reality. So we say here it's Hurwitz type, and we call that because actually we somehow generalized this the theorem by Ganmacher, and we call that because we were thinking about the Hurwitz matrix polynomial. So Hurwitz matrix polynomial will be in the case when the determinant of this matrix will have all the roots in the half side of half line. So this is the determinant. So, but we will recall this definition later. So now we can first look at a certain asymptotic relation of this on the left-hand side, and we have 20, 21. From that, we obtain a relation between the moments and the coefficients of the polynomial. So we so here's in the center, and then we use some notation. With the help of some notation, we actually prove that the H part is actually a orthogonal polynomial P1, and HA is the second kind polynomial of this P. So in a similar way, so in the case when n is even, so the degree is even, then the G part of the polynomial is P21, and Hn is Q2m. So in this sense, so this was important. So this with this fact we connected actually there. We connected the family of orthogonal polynomials for the family of Hurwitz polynomials in the matrix case. So here is one lemma. So let be F be a matrix type polynomial, then there exists a positive sequences of these moments or Markov parameters. They are also called Markov parameters. We recall that we are not here writing the alpha, but the alpha is there, so it should be there. We just don't write it. So we have this the equality. So again, if there exists two sequences, then this equality 52 holds, and where P and Q and Q P1, P1m, Q1m, and are constructed by these moments R and P, so respectively P2m, Q2m are constructed by these moments. So then this is a relation. Then given the moments, we construct the polynomials, and then we set this expression, and we can see that actually this is Hurwitz polynomial. So in the opposite, if we have this, let be this these polynomials given, so then constructed by they are constructed with the moments, positive moments, and then the polynomial is Hurwitz type. So, and again, here we recall only that with this number of moments. So we have this representation so in the continuous type form for this we have actually two representations, and then we have theorem. Then let be these four polynomials be given, and which are constructed with the moments. So recall that the P1m and P2m are orthogonal polynomials, and Q1m, Q are not orthogonal with respect to sigma, but they are orthogonal will be orthogonal with respect to other measure. Well, these polynomials then for alpha from the set, Fn is Hurwitz matrix type polynomial if and only if this representation satisfies 54. So one application, immediate application for alpha equal to 0 in this current case, it's the following theorem. So system, this is an ODE linear system. So this is a matrix, so constant matrix. So so in engineering and also in the undergraduate studies, we were interested about the stability of this system. So then the system is asymptotically stable in the Lyapunov sense if normally if the zeros of the characteristic polynomial have a negative real part. So this is typical stuff on the undergraduate course, and we could reformulate this theorem in the sense for results. So the system is linear ODE system asymptotically stable if only if the characteristic polynomial has the representation of 55. So it means someone is familiar with polynomials, and we could maybe identify immediately that this would be Hurwitz polynomials, as in this sense. So, well, some remarks about the Hurwitz matrix polynomial. So a matrix polynomial F is Hurwitz stable if the set of all zeros of the determinant belongs to the left half so side of the complex plane. So this is a definition. So the fact that the matrix Hurwitz type polynomial is a Hurwitz polynomial was considered by these two authors in 21. But at the same time, we should notice that the set of matrix type polynomials do not constitute the entire class of Hurwitz matrix polynomials. So this is written in some paper under review, here written. So an example is this matrix. So that's 56. The determinant is the 57, and the value of these roots, approximate value, are then 58. So then we see that this 56 polynomial is actually Hurwitz polynomial, but this matrix not matrix Hurwitz type polynomial, because if we take the H and G part and we make the asymptotic expansion, then we'll have the moments. The moments will not be Hermitian. So then we cannot apply our method. So another example, we take a density like that in the slide. The marker parameters are written here, so we can calculate the P11 polynomial. Q11 polynomial, this one, and the polynomial F2 is as 60. So we see here that actually the coefficients are not real. So this is interesting, because usually so one part of the people who studies the polynomials in the scalar case, they consider a real polynomial. So but our polynomials can be complex one. So but the determinant are real. So here real. And well, we have done this polynomial as Hurwitz actually. So for every alpha. So about Hurwitz polynomials in the matrix case, what one can find in some information in the book by Lehrer and Timinetsky, in this work written in the bottom of the slide. So then before the references, then as a conclusion, we have generalized, we'll try to generalize the Toda equation in the matrix case, and also the Hurwitz polynomials in the matrix case. Here are some references we can mention, and that's it. Thank you.
Thank you, Abdon. Are there any questions for our speaker? Well, if there are no questions, perhaps we can thank our speaker and conclude our conference today. And we will resume on Monday. So we're not going to be meeting tomorrow. We will resume on Monday at 9 a.m. Mexico City time. Ricardo, do you have anything to add?
Just if there are no further questions or comments, and no one wishes to say something, I guess I will wish all of you a good, nice weekend. And then we see each other, as Tunja said, Monday at 9 a.m. Mexico City time. And then I should close the Zoom connection. And okay, see you Monday then.
Bye.